Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams, and today I want to get back into the Fermi paradox and discuss another proposed resolution that has been made over the years, and it's one that I've come to refer to as the brief window hypothesis. Or to put it another way, it's an umbrella term that embraces different aspects of a number of different proposed resolutions, not the least of which are the Great Filter hypothesis, the Transcension hypothesis, Sagan's response, and also the notion that intelligent life may be prone to self-destruction. So to recap, Fermi's paradox came to be framed by Michael Hart and Frank Tipler, two astrophysicists, who argued between the mid-70s and early 80s that humanity should have heard from extraterrestrials by now. The fact that we haven't, and the fact that we see no indication of extraterrestrial civilizations that have populated our galaxy or other galaxies, that this is the strongest indication that humanity is in fact alone in the universe. And this has prompted many rebuttals over the years. In particular, Carl Sagan and his colleague William Newman, they published what has come to be known as Sagan's response, in which they argued that the fact that humanity hasn't heard from extraterrestrials yet cannot be construed as evidence that none exist out there, that there's any number of reasons why humanity may not have heard from an extraterrestrial civilization, and many of those possibilities have been explored in scientific papers that have been published ever since. And to this, the brief window hypothesis essentially states that there may be a time limit on how long civilizations can be expected to send transmissions to space, either deliberately or inadvertently, and that if you're not listening at exactly the right time within that brief window, you're going to miss them. And as I said, this idea borrows from several other proposed resolutions. One of these, which is very relevant to the discussion today and the topic of the brief window hypothesis, is the Great Filter, which was proposed by Robin Hanson, which we discussed in a previous episode. So Hanson's argument was essentially that if we accept that life in the universe must be ubiquitous, that it would be everywhere in abundance, just like the ingredients for life, and if we also accept that we have not heard from any extraterrestrial species, we have not found any evidence of it, which so far does seem to be the case, then there must be something that prevents life from evolving to the point where it reaches a complex state of development and advancement, and where it would be in a position to travel throughout the stars and be noticed or communicate and be heard. And in his seminal paper, The Great Filter, Are We Almost Past It?, he essentially argued that wherever you place that filter along the evolutionary and developmental timescale, from simple single-celled bacteria all the way out to a species that has developed language, technology, is spacefaring, and has advanced communications, depending on where you place that filter, that has drastic implications for humanity, because we may either be past the filter or on our way towards it. And similarly, a lot of researchers have explored the idea that maybe intelligent life is prone to self-destructive behavior. Using human history as a template, we see the threats today facing us are nuclear war, environmental destruction, overpopulation, and outstripping our resources. And ever since the industrial era, there have been dystopian style narratives and apocalyptic style narratives that were inspired by a pessimistic appraisal of our future. And it's entirely possible that this is what happens to all intelligent species. Sooner or later, they don't pass evolution's test because their intelligence comes at the expense of too much growth, and they inevitably outgrow their resource base, or they end up turning on each other, fighting over diminishing resources, and they employ nuclear bombs, and that put an abrupt end to their civilization. So if we accept that these types of situations, these scenarios, are typical of intelligent life forms, if we are in fact not the only species that has been known to ruin its environment and constantly build bigger and badder weapons, where our technology eventually outgrows our wisdom, then it is a safe assumption that civilizations only exist for a certain amount of time before they inevitably succumb to violence or self-destruction. And this, in effect, is the window. So if we don't pick up radio transmissions from a species within a certain amount of time, we will have missed them forever. And this brings to mind another very key point in the search for extraterrestrial intelligence, and that's known as the Drake equation. And this is named after famous SETI researcher and astronomer Frank Drake, who conducted the very first SETI experiment called Project Ozma in 1960. And this consisted of Dr. Drake and his colleagues using the radio telescope at the Green Bank Observatory in West Virginia, and they used it to listen to Tau Ceti and Epsilon Eridani, which are two nearby sun-like stars and are considered pretty good candidates for having habitable planets around them and possibly giving rise to life and advanced life. Now, the survey was unsuccessful, but nevertheless, it set a precedent. It got the ball rolling on the entire field of research. And a year later, Drake was hosting a symposium with fellow SETI researchers and radio astronomers, and to prepare for this meeting of the minds, he drew up an equation that encapsulated all the challenges that SETI researchers face, and it came to be known as the Drake equation. And what it essentially states is that the number of extraterrestrial species in our galaxy that humanity could communicate at any given time, well, in order to figure out that number, which he defined mathematically as n, you had to multiply the rate of star formation in our galaxy times the number of stars that have planets orbiting them times the number of stars that are likely to have planets that can give rise to life on them, multiply that by the number that could give rise to advanced life, and so on, technological activity, and last, by the length of time, defined mathematically as a big L, that extraterrestrial species would send transmissions to space. Now, of course, the interesting thing about this was not meant to be any actual mathematical formula. It was a thought experiment. Basically, it was saying that this is what we're up against. And all of the parameters were incredibly vague at the time. Even today, of course, we have gotten a better idea about some of these parameters, especially where the number of exoplanets in our galaxy is concerned. We have a much better idea. But the rest are all subject to huge uncertainties. We have no idea how many planets out there statistically are likely to give rise to life, or how much of that is likely to advance to a stage where it could actually communicate with other intelligent species. And above all else, we have no idea how long a civilization would live for. That's really the interesting question there. That's really the most uncertain and consequential aspect of the Drake equation, at least for the sake of the brief window hypothesis to many resolutions of the Fermi paradox. L is the most important parameter. How long could we expect a civilization to broadcast for? So as I said, this theory does borrow from other proposed resolutions. It touches on a number of theories as to why SETI is so very difficult, why we're confronted with the Great Silence. But it takes those a step further by saying that longevity of a species is defined as the amount of time before a civilization destroys itself, or condemns itself to starvation and collapse. So running with that metaphor, the window opens around the time when a species develops the capacity for radio communications and begins broadcasting them to space. As long as that civilization is transmitting to space, we would be in a position to hear from them. Minus, of course, the time lag. The amount of time it would take for radio waves to propagate through space and reach us, that comes down to how many light years away the civilization is. So if we were to use an example and say the civilization that is communicating, it's just putting out broadcasts, they're 1,000 light years away. And they have been alive for 1,000 years before they succumbed to whatever fate. So for a period lasting from 1,000 years from now to 2,000 years from now, that would be the time period in which we could hear from the species. But once the transmitter is dead, and the last of those radio waves have left their planet, 1,000 years later, when that last transmission reaches us, the window is effectively closed. If we haven't picked up on anything that was broadcast in that time, we never will. We're never going to hear those radio waves reverberate back at us. There aren't going to be any repeat broadcasts or reruns. And as proposed resolutions go, this is a pretty good one. It does basically state that communications with any advanced species in our galaxy, it's a matter of precise timing, it's a matter of us being in a position to pick up transmissions from space, that we would be advanced enough to hear, interpret, decode these messages, and us being around long enough to sort of catch the wave. A wave being defined as an expanding sphere or shell of radio traffic. As it expands farther and farther away from its system, sooner or later we pass through the outer edge and then into the inner edge of it, and it's gone forever. And of course, these transmissions that we're talking about here, they need not be deliberate. Fact is, here on Earth, we have been broadcasting radio transmissions to space for about a century that were powerful enough to propagate through space for hundreds, if not thousands of light years and beyond. But there have also been attempts to message space. And this goes by the alternate name of active SETI, where you're broadcasting rather than listening, aka passive SETI, or messaging extraterrestrial intelligence, which goes by the acronym METI. And this has emerged in its own right as a separate field related to SETI, but with entirely different considerations, parameters, and of course, there's the whole question of ethics, and it's controversial, understandably. And our efforts to do this ourselves have been quite limited. The best example is the Arecibo message, which was sent from the Arecibo Observatory in Puerto Rico, which was the most powerful radio telescope in the world for decades. And this transmission was sent out in 1973 towards the Messier 13 star cluster, which was considered there too a pretty good candidate for hosting at least one civilization. But these and all other efforts, they really pale in comparison to passive SETI. And for obvious reasons. The aforementioned controversy, the question of ethics, and taking unnecessary risks. Now, the difference between METI and just radio traffic that's spilling out into space is that METI is focused and directed. Right? The Arecibo message was sent to the M13 cluster. Radio propagation would mean it could be heard from other locations. There'd be spillover, but the intended recipients would be located in that cluster. This too presents a very significant challenge in that for a civilization to hear it in much the same way, in order for us to hear a transmission that was directed towards Earth and the solar system, our radio antennas would need to align with it. So there's still a chance we could pick it up, but the best case scenario would be that we just happen to get the timing right and accidentally line up our receivers towards a certain star system as it's broadcasting. So no matter what, picking up transmissions from space is very difficult, it's very complicated. And if we add to that the fact that those transmissions are only going to be happening for a set amount of time, and we can't say exactly how long, but if we accept that there's a window, that is another complicating factor. And from that, we're essentially saying that the most important parameter in the Drake equation Especially when it comes to resolving Fermi's paradox, it's L, it's longevity. And this raises another very interesting point. Transcension hypothesis comes into this too, because if we look at the history of human technological development, right now we are at a point where communications are evolving far beyond the use of radio waves. We've gotten into the microwave domain, we've gotten into the directed energy domain. We rely on focused electromagnetic energy in order to send information, and so much of that still runs on radio waves. But there could be a time in the near future where we ditch that in favor of laser communications, in favor of microwave communications, in favor of quantum communications, where entangled photons transmit information instantaneously by having their properties beamed from one place to the next. That way, instead of waiting on the speed of light to deliver our information to us, we could establish instant transfer across distances of varying scale. We're not sure how far we could send it, but the point is, if and when those technologies become very, very common, the use of radio signaling, it will either become much more rare or possibly even non-existent. So this opens up another interpretation of the brief window hypothesis. Maybe civilizations are limited to the amount of time in which they can send out certain types of technosignatures. If, in fact, technology is subject to accelerated returns for every species, as it certainly is with us, that Radio SETI has a window on it. That there's only a certain amount of time before the extraterrestrials stop broadcasting in the radio spectrum, not because they're dead, but because they've evolved further. And so in this respect, this proposed resolution, it takes into account another proposed idea for Fermi's paradox and interprets it in the parameter of L. It's not that civilizations die at this point, but rather that they transcend, evolve. They become something that we no longer know how to look for because our SETI methods are looking for technology that's too specific. So this is why, of course, SETI researchers have been lobbying for a long time now to expand the net, to look for different types of technosignatures. In 2018, NASA put out its technosignature report, which I know I mentioned in a previous episode, and it included several possible technosignatures that researchers should be looking for in the future. Radio is still considered fair game. Any transmissions we pick up would have been sent at the time that they were sent by a civilization that was well into its industrial phase and was probably reaching the cusp of becoming a digital age civilization, but that we should also be looking for directed energy communications, possibly neutrino communications, and even gravitational wave communications. It's like any form of energy in the universe, any form of subatomic particles, any form of disturbances to the fabric of space-time that travel at the speed of light, if they can be structured, then they are a potential means of communication. We should be looking for them. But we also need to be wary of the possibility that there's a clock on all of them. Civilizations pumping out radio waves for a few centuries, or 1,000 years even, that seems reasonable enough. But at a certain point, they're going to either stop transmitting or they're going to flip their transmissions to some other higher order technology. But of course, the window cuts both ways. It's only as long as we are still alive here on Earth and still capable of listening to the cosmos for various types of technosignatures that we are going to be in a position to pick them up. If we ourselves succumb to some cataclysmic fate, then the window will have closed on us. It's also possible we could evolve in the distant future to the point where we no longer care about contacting other civilizations, or we're frightened that we might cause irreparable harm to them simply by engaging with them, in which case we'll have shut the window ourselves. Like all other proposed resolutions, it's very fascinating. It really makes you think, And it has the potential of really just turning your brain inside out because, of course, it's always plagued by the question of how do we know any of this? How do we know that this applies to intelligent life out there when we are the only, as far as we know, species capable of communicating in a way that could be picked up in space on other planets? We're by no means the only intelligent species here on Earth, and it's incredibly anthropocentric to think so. But as far as we know, we are the only ones who could conceivably engage with intelligent life on another planet, because we are the only one that relies on advanced transmission technologies. And so, as always, we are projecting ourselves out there in the hopes of finding out what's there and hoping it'll talk back to us. And it's only by actually finding it that we're ever going to be able to fix this frame of reference problem and start thinking in terms of, well, this is what intelligent life does. We know this because we've seen it in countless different examples. And yes, as I've said before, the coming years are going to be very exciting because a lot of these theories are going to be tested out. Breakthrough Listen is the most ambitious SETI project ever mounted. It's being run by Breakthrough Initiatives. It has some of the most advanced radio telescopes in the world and the best data analysis going on. And they are actively searching through terabytes of data and producing regular updates, basically to keep the scientific community and general public apprised of any possible detections. In addition, our fascination with unidentified aerial phenomena, that has not gone away or diminished at all. In fact, it's reached overdrive because of all the information that's been made public in the last few years. And there's even an initiative similar to Breakthrough Listen called the Galileo Project, which is looking at all of the data collected by premier observatories and scientific institutes around the world, looking for evidence of possible interstellar visitors and possible extraterrestrial spacecraft in our atmosphere. And of course, looking for the telltale indications that these are, in fact, things that are not of this world. Exciting times lie ahead. So, thank you for joining me for another installment in this ongoing segment on the Fermi Paradox. Join me next time where we'll discuss percolation theory and how the fact that space is hard may impose limits on just how far civilizations can expand. And that maybe this is why we're not detecting or have heard from an advanced alien species by now. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.